Thank you for a great introduction. My today's talk is about adversarial robustness. I'm going to cover two aspects, background knowledge and two case studies on how to apply the adversarial robustness. Let's go to the point one first. Adversarial attack can evaluate the vulnerability of machine learning model. Why? It is because machine learning models are very sensitive to the input perturbations. For example, with only small noise, the image of pig will be wrongly recognized as an airline. How to construct the adversarial data? We basically solve a constraint optimization problem. Given a machine learning model and its loss function, we output an adversarial data, maximizing the loss within the null-ball constraint. The null-ball constrains the same semantic meaning between adversarial data and its natural data. The epsilon controls the size of null-ball. Project gradient descent, PGD, approximately solved this constraint optimization problem. Given a starting point, PGD calculates the gradients of this loss function with respect to the input. Gradient is a direction pointing to a place with a slightly larger loss. Now, we get a new point whose loss is slightly larger than the natural data. Then we calculate the gradient again. The loss of yellow point is again larger, so on and so forth. Finally, we get a red point, which can make machine learning model inaccurate. Why the machine learning model are so vulnerable to adversarial attacks? It is because standard training outputs a model whose decision boundary is near the data. Therefore, when we slightly perturb the near decision boundary data, the model will make mistake. Even worse, due to the curse of dimensionality, almost all data are near the decision boundary. To meet the above challenge, we have a new style of learning strategy that is adversarial training. Adversarial training has two purposes. First is to correctly classify the data, that is increasing natural accuracy on natural test data. Second, unlike those standard training, adversarial training outputs a thick decision boundary whose data are further away from the decision boundary. The learning objective of adversarial training is minimax formulation. Inside, there's a maximization. We commonly use PGD to generate the adversarial data within the null ball. Outside, there's a minimization, where we find a classifier to fit those generated adversarial data. To realize this learning objective, we use alternating optimization technique. At each epoch, adversarial training conducts step 1 and step 2 alternatively. Step 1 to generate the adversarial data using PGD method. Step 2 is to minimize the loss on the generated adversarial data. In comparison, at each epoch, standard training minimize loss on the natural data with respect to the model parameters. Next, I'm going to cover two case studies on how to apply the adversarial robustness. We understand that adversarial attack is a way of uncovering the vulnerability of machine learning model, and adversarial training is a way of making those machine learning model robust against those attacks. Therefore, I will show two case studies using the attack to evaluate the vulnerabilities and using the adversarial training to enhance the adversarial robustness. I'm going to give two examples, deep image denoiser and non-parametric two sample test. Image denoising is reconstruct the clean image from their noisy observations. Therefore, it is commonly used in medical image, satellites, and camera. In image denoising, the noise is generally considered to be a random variable with zero mean. For example, if we can take a large number of pixels and compute their average, the noise should be cancelled out. Otherwise, the noise will affect the brightness of the image. Because of this zero mean property, traditional method in OpenCV commonly use the non-local mean denoising. The idea is simple. Given an image, we find a similar patches, then average out the noise. Now, we go to the machine learning time, and we need to learn a good image denoiser. Specifically, the image denoiser is denoted as a deep neural network, taking input the noisy images and giving output a clean image. However, in practice, we only have clean images as the training data. To solve this, we construct the noisy image by adding Gaussian noises with zero mean of various levels. Then we can have a deep image denoiser that can perform much better than the non-local mean denoising method. However, although deep neural network has good performance, it is vulnerability to adversarial attacks. Similarly, this also applies to the deep image denoiser. To explore this, we ask a research question. What kind of zero mean noise that makes deep image denoiser fail? To answer the above question, we design zero mean adversarial attacks to evaluate the vulnerability of deep image denoiser. To realize this attack, we use PGD method. But this PGD method have to meet two constraints, which is different from the conventional one. First, the noise should be bounded by the adversarial budget. Second, the noise should meet the zero mean property. To realize this, we customize the projection function in the PGD method. And the most interesting part is the projection pi that meets the two constraints. To meet the zero mean property, the projection function pi should project the adversarial noise onto the zero mean plane. The zero mean plane consists of vectors z whose means of its elements equals 0. How could we project a vector delta onto a plane? First, we're going to find an all one vector that is orthogonal to this plane. That's the zero mean plane. Then we project a vector delta along the direction of this all one vector. Then the adversarial noise delta minus this new projection leads to a new vector that is on the zero mean plane. Therefore, the black vector is what we want. Now, we have our two-step projection pi. The first step is to meet the zero mean constraint. The second step is to meet the adversarial budget constraint. For example, we can see here, the deep image denoiser can effectively handle the noisy, normally noisy image and remove the noise to reconstruct the clear images. By comparisons, if the noise is crafted by our zero mean attacks, the performance of the deep image denoiser is severely destroyed. We can see some blurs on the roofs and some strange contours in the sky. Therefore, our zero mean attack can indeed uncover the vulnerability of deep image denoiser. Next, can we make the deep image denoiser robust? The solution is adversarial training. We add an additional loss term to encourage the output of adversarially noisy image to be similar to the output of normally noisy image. Therefore, we train a deep image denoiser using both adversarially noisy image and naturally noisy image to ensure the reconstruction quality is high and the reconstruction is robust. To realize this learning objective, we alternatively use the PGD method to generate the adversarial noise and then minimize the above two loss terms with respect to the model parameters. Then we found, compared to the standard training, our adversarial training can ensure the reconstruction quality under attacks. Last but not least, we surprisingly find that robustness of deep image denoiser can also benefit the generalization capacity on unseen real-world noise. In other words, the robust deep image denoiser can denoise the real-world noise even without training on the real-world noisy image. We guess it is because adversarial attacks can exploit the worst-case noise. Learning from those worst-case noise can make deep image denoiser deal with various types of unseen noise. I saw some questions on the chat box. I'm going to answer it later. Yeah. Okay. Let's look at another example. Two-sample test. Two-sample test is a statistical hypothesis testing, judging whether the two sets of samples are drawn from the same distributions. It is widely used to analyze the critical data in physics, chemistry, biology, so on, to check whether their scientific experiments have made significant changes or not. How to test? We firstly define a test statistic. The test statistic measures how different the two batches of data are. Then we compute the p-value. P-value is the probability of observing this test statistic given the null hypothesis. The null hypothesis means the two distributions are the same. If this probability is very low, we're going to reject this null hypothesis. Let's look at an example. We have two batch of apples of various size from two companies. We really want to know whether these two batch of apples have the same quality. Firstly, we calculate the test statistic. This is a t-test. XP bar is the average of these 5 apples. SQ bar is the average of these 5 apples. Sigma P is the standard deviation of these 5 apples. Sigma Q is standard deviation of these 5 apples. NP equal to 5, NQ equal to 5. Suppose we get a value of minus 2.44. We really want to know whether this value is large enough to tell any differences. Therefore, we look at the distribution density function of this test statistic. We found that the probability of this test statistic under the null hypothesis is very low. For example, probability is 0.024. Then we cannot accept. We have to reject the null hypothesis and conclude that these two batches of apples are different quality. In practice, t-test is very limited, which cannot handle the complex distributions. Therefore, we need to use the general purpose test statistics. However, computing quantiles of general purpose test statistics under the null hypothesis is very tricky. To solve this, we estimate the quantiles using the permutation test. Under the null hypothesis, we randomly shuffle the joint set of SP and SQ into S1 and S2. We can treat S1 and S2 set coming from the same distribution. And then we compute the test statistic of S1 and S2. Then we repeat. For example, we repeat this process 1,000 times. We can plot the empirical CDF of this test statistic under null hypothesis. Finally, we can locate our test statistic of SP and SQ here. 1 minus this value is our calculated p-value of this test statistic. Now, I will introduce a general purpose test statistic, maximum mean discrepancy, MMD. MMD measures the differences between distribution of P and Q, which is the largest differences in expectation over all functions. However, we have limited data. We must restrict the function class to provide powerful finite sample estimates. But we also want this function class to be rich enough to be flexible. Therefore, we choose this function class F to be the unit ball in a reproducing kernel Hilbert space, RIKEN-AIP. Then we define the kernel mean embedding to embed the distributions into infinite dimensional feature space. This can allow us to compare and manipulate the distribution using dot products. And due to the reproducing property in RIKEN-AIP, we can make the soup disappear and use the kernels to calculate and compare two distributions. If the MMD equal to 0, the two distributions are the same. We actually can use the many and different estimation to estimate the MMD. let's make notation simple. We denote MMD square hat estimation by kernel K parameterized by theta, like this. Then how to test? First, we fix a kernel and its parameters, such as Gaussian kernel and its length scale. Then, given SP and SQ, we calculate the estimation of MMD. This is test statistic. Then we use the permutation test to estimate the p-value of this calculated test statistic. Lastly, we're going to reject the null hypothesis if this p-value is too small. Otherwise, we accept the null hypothesis. Now, we go to the machine learning time. We should learn the kernel parameters from data. We can use deep kernels, and the theta is parameterized by a deep neural network. How to learn the parameter theta? First, we split the data SP and SQ into the training set and test set. Second, we define a learning objective and optimize the deep kernel. Then we conduct two sample tests using these optimized deep kernels. The next question is how to define the learning objective for learning the optimized deep kernel. The learning objective is the test power. The test power is the probability of rejecting the null hypothesis, and the alternative hypothesis is true. Due to the asymptotic of MMD and the alternative hypothesis, we use the central limit theorem. R is the rejection threshold decided by the permutation test. Big sigma is the CDF of standard normal distribution. Then for large N, the test power is dominated by the first term. To compute the first term, we estimated using the kernel operations, which is parameterized by the theta. Finally, we can obtain the optimized deep kernel by maximizing the test power on the training data. Then the two sample test will have a very powerful testing ability with this optimized deep kernel. Now, we consider a potential risk that causes a malfunction of a non-parametric two-sample test. To this end, we use PGD method to minimize the test power to search for the adversarial test pairs. For example, we have a lovely image of cats and dogs. The non-parametric two-sample tests can correctly differentiate the benign pairs of cats and dogs coming from the different distributions. But they will wrongly judge the adversarial pairs coming from the same distribution. Almost all the two-sample tests think this dog and cats coming from the same distribution. Clearly, this is wrong. To robustify the non-parametric two-sample test, we propose to adversarially learn the robust kernels. In particular, this defense is formulated as max-min optimization which has a similar taste of adversarial training's minimax formulation. For its realization, we interactively generate the adversarial pairs by minimizing the test power in inner minimization and update the kernel parameters by maximizing the test power on the adversarial pairs in outer maximization. Therefore, we can obtain the robust kernel. And two-sample test with a robust kernel can resist against adversarial attacks while maintaining the good test capacity. The take-home message is traditional method has limited performance. Recently, we have machine learning method which have good performance but are vulnerable. Now we really should have robust machine learning methods that have a good performance and are robust. Thank you. If you have any questions, please feel free to open your mic to ask. I saw some questions on the chat box. How to define the failure of the denoising task? Basically, they have some scores. They have some scores on define the success of the denoising. That means the comparison between the clean image and noisy image, reconstructed image. They have, for example, the MAE error. We basically can use this metric. If this error become larger, we can see the reconstruction quality is damaged. So yeah. Hope I answer your question.
Thank you for answer. So may I speak directly? So I think, can you hear me, Jingfeng?
Yes, I can hear you. I can hear you. Yeah.
So unlike the classification problem, we can easily see that your attack is successful if the classification label is wrong. But for denoising task, I think the reconstruction error, it's not easy to see this attack is successful or not. So I just curious how you define your attacker is successful. Do you need some kind of threshold to
you can think about this? There are no such threshold. You can think about the loss, like regression loss. If your attack can make the regression loss significantly bigger, we can be confident that the attack is very effective. So yeah, we don't have the threshold to judge. When this is large enough, we see this is successful. We can see here the attack is effective. Yeah.
Okay, so thank you.
It's also applied to here. Yeah.
Maybe may I ask another question? So
sure.
I think you use deep learning to do denoising, and when you do the training, you assume the noise is Gaussian distribution, right?
Yeah, follow others works.
Yeah,
right.
But when you do attack by adversarial attack, I think you put a perturbation which is not follow Gaussian distribution. That's why the result is. Yeah. So how about if you train your model again by like new distribution noises?
That is what we did actually, because the noise in the deep image denoising have to meet the zero mean property. That's it like this. Otherwise, the noise will affect the brightness of the image. Therefore, our adversarial noise also have to meet the zero mean property. So to make it robust, actually, this is what we did in our adversarial training strategy. This is follow the Gaussian noise. this follow the adversarial noise that is coming from the new distribution. Just now you mentioned. Therefore, just adding a new loss term to encourage the adversarial noisy image to be similar to the Gaussian normally noisy image. Yeah, this new term, loss term.
So first of all, I would like to thank the organizer for organizing this workshop. So today I will present my research on exact statistical inference for the Wasserstein distance by select inference. So this is a joint work with my supervisor Ichiro Takachi. So this is just a brief introduction about myself. So I'm Vo Nguyen Le Duy. So currently I'm a PhD student at Nagoya Institute of Technology. So I'm also a junior research associate at RIKEN. So my research interests including statistical machine learning, hypothesis testing, and select inference. So this is the outline of my presentation. So it includes 3 parts. So in part 1, so I will point out the reliability issues problem in machine learning with an example on the Wasserstein distance. Then in part 2, I will present a select inference framework, so which is recognized as a new promising approach for quantifying the uncertainty or statistically guarantee the reliability of the data-driven machine learning result. And finally, in part 3, I will present an approach to quantify the uncertainty of the Wasserstein distance by using the concept of the conditional select inference. So now let's start with part 1, uncertainty in machine learning. So nowadays, machine learning algorithms have been developed as a powerful tool for data analysis tasks, and is used in numerous domains. Unfortunately, the results of the obtained from machine learning algorithm might be too overfit to the data, and we might obtain a lot of false discovery. So using these false results are harmful for high-stake decision-making in a lot of practical applications. So for example, medical diagnosis or automatic driving. So this is an example in the case of the Wasserstein distance. So the Wasserstein distance is a metric used to compare the probability distribution. So the Wasserstein distance measures the cost to couple one distribution with another distribution. So this distance arises from the notion of optimal transport. So this figure, so an example is shown in this figure. So given the data, the source targets in blue and the targets, the source instance in blue and the target instance in red. So our goal is to compute the Wasserstein distance between the source instance and the target instance. So first we input the data to a linear program, and then we obtain the transportation map. So finally, then based on the transportation map, so we obtain the optimal coupling between the source instance and the target instance. So here, the orange line is the optimal coupling between between the source instance and target instance. And finally, based on this optimal coupling, we can obtain the Wasserstein distance. So the Wasserstein distance has attracted a lot of attention and has been used in various machine learning tasks. So the utilization of the Wasserstein distance benefits to several applications. For example, it can be used as a loss function in a supervised learning, generative modeling, or computer vision. But unfortunately, when the Wasserstein distance is uncertain when it is calculated under the noisy environment. So more specifically, when the Wasserstein distance is calculated from the noisy data, the uncertainty in the optimal coupling leads to the uncertainty of the Wasserstein distance. So this is because the Wasserstein distance is calculated based on the optimal coupling. Therefore, it is highly necessary to quantify the statistical reliability of the Wasserstein distance when it is used for the practical application or used to make the decision in high-stake decision-making problem. So one way to quantify the statistical reliability is to provide the confidence interval for the Wasserstein distance. So reliability of machine learning has been discussed for various aspects. So for example, that is statistical inference, including hypothesis testing, confidence interval, adversarially, fairness, and robustness. In statistical inference, there are mainly 2 approaches: frequentist approach and Bayesian approach. And in infrequentist approach, there are also mainly two types of conducting the inference. That is non-asymptotic inference and asymptotic inference. And in these studies, I will mainly focus on the frequentist-based exact statistical inference. So our goal is to provide the non-asymptotic exact confidence interval for the Wasserstein distance. So the confidence interval is well known as a fundamental approach for reliability quantification in science. So a confidence interval is a range of the value that we are fairly sure that the true value of the unknown parameter of interest lying. So this is the general recipes for constructing a confidence interval. So first, we need to identify the unknown parameter of interest. And then at the second step, we need to construct a test statistic, which is a function of the data. The test statistic here can be seen as the observation of the unknown parameter. And finally, the confidence interval of the unknown parameter is computed based on the test statistic that we identify at the second step. Here's the main challenge is how to compute the valid confidence interval for the data machine learning result. So the question is why it is challenging? Why is it difficult? So in traditional method, the traditional confidence interval computation is simple. This is because of the parameter of interest is predetermined before we collecting the data. So therefore, no data selection bias exists. But in contrast, in machine learning, so we first collecting the data and then applying the machine learning algorithm on the data to observe the parameter of interest. So in other words, the parameter of interest is data driven and defined after collecting the data. Therefore, data selection bias exists, and we must and proper bias correction is required to compute a valid confidence interval for the data machine learning result. So there are some existing methods for correcting the selection bias in data-driven machine learning. The first one can be multiple testing, multiple comparison, for example, morphology correction. But unfortunately, in this scenario, multiplicity is unrealistic because a huge number of possible hypotheses can be generated by the machine learning algorithm. For example, in the case of the Wasserstein distance, if we want to use multiple testing comparison to correct the selection bias in the Wasserstein distance, we need to enumerate all possible coupling between the source instance and the target instance. So which is unrealistic and unfeasible because we cannot generate all possible coupling. So another approach is the data splitting. But however, in the data splitting, the information in the data is wasted. So we lose the power. Both in selecting and evaluating the data-driven hypothesis. Besides, the data splitting is also not applicable for several tasks such as unsupervised learning or representation learning. So this is the summary of part one. So although the literature related to machine learning algorithm is huge, so less attention has been paid to statistical reliability of the machine learning result. Confidence interval is well known as a fundamental approach for reliability evaluation. However, there is no general and practical framework that can properly compute the confidence interval for the data machine learning result. So in the next part, I will present a new promising approach to compute the confidence interval for the data-driven machine learning named conditional selective inference. So now let's move to the part two, conditional selective inference. So selective inference has been recognized as a new promising approach to access the statistical reliability of the data-driven machine learning. The basic idea of conditional selection is that we will make the inference conditional on the event that the parameter of interest is identified by machine learning algorithm. Then by doing the conditional inference, the valid confidence interval can be computed. So this is the picture. So we first collecting the data, then the applying machine learning algorithm on the data to identify to obtain the parameter of interest. And after that, we construct the test statistic, and finally, the confidence interval is computed by using conditional selective inference. So this is the concept of the selection inference by schematic illustration. So given the observed data, this is observed, we first applying machine learning algorithm on the observed data and obtaining the hypothesis A. So in the case of the Wasserstein distance, hypothesis A can be corresponding to the optimal coupling on the observed data. And then we will try to search at the second step. We will want to search the region where the same hypothesis A is obtained. So for example, in this figure, when we apply machine learning algorithm on the purple data point, we obtain the same hypothesis A as the observed data we observed. And therefore, the reason that we want to identify is the region that containing all these purple points. And finally, at the first and final step, the confidence interval is computed by considering the conditional sampling distribution of the test statistic, conditioning on the conditional data space that we identify at the second step. So by doing the conditional inference, we can remove the selection bias in the data-driven machine learning, and we can conduct exact statistical inference for the data-driven machine learning result. So up to now, I've already presented the main concept of selection inference. So here is a summary of part 2. So selection inference has been actively studied as a promising approach for statistically quantifying the reliability of data-driven machine learning results. A valid confidence interval can be computed by conditioning on the event of the event that the parameter of interest is selected. So in other words, by conditioning on the selection event, the exact sampling distribution of the parameter of the interest can be analytically identified. So this is the general framework for quantifying the reliability of the machine learning result. So first, we initially collect the data. Then at the first step, we apply machine learning algorithm on the data to obtain the parameter of interest. Next, constructing the test statistic, and finally, the valid confidence interval is computed by using the concept of conditional selection inference. So now I will move to the part 3 of the presentations. So in part 3, I will present an exact statistical inference method for the Wasserstein distance by using the concept of the conditional selection inference. So here, consider the two observed vector X observed and Y observed sample from this model. So here, capital X is the random variable, mu of X is the true vector, and epsilon X is the Gaussian noise. Similarly applied to the Y. And X observed can be seen as the blue data points, and the Y observed is considered as the red data point. And then after observing the data, we apply a linear program on this data and obtain in the optimal coupling M observed, script M observed. So this is the optimal coupling. So the optimal is represented at the orange line. And after obtain the optimal coupling, we can easily compute the Wasserstein distance. And then our goal is to provide the confidence interval for the Wasserstein distance that we compute at the previous slide. So here, the confidence interval is considered to be valid if the probability that it can cover the true value of the Wasserstein distance is equal to 1 minus alpha. So here, 1 minus alpha is the confidence level and given by the user. Unfortunately, constructing the valid confidence interval for the Wasserstein distance is challenging because the optimal coupling is selected based on the data. So in traditional method, we need to fix the optimal coupling in advance. But in the case of data-driven machine learning, the optimal coupling is decided based on the data. Therefore, to compute the valid confidence interval for the Wasserstein distance, we need to remove the data selection bias. So in other words, we need to remove the selection bias of selecting the observed optimal coupling. So finally, therefore, we introduce an approach to remove the data selection bias by in the case of Wasserstein distance based on the concept of the conditional selection inference. So this is the proposed idea. So we propose an approach to avoid the data selection bias by considering the distribution of the Wasserstein distance conditional on the optimal coupling. So here, more specific here, x and y is any random vector, and script aim of x and y denote the optimal coupling between any random vector x and y. And here, by considering the sampling distribution of the Wasserstein distance conditional on the space where we obtain the same optimal coupling as the observed data, then we can successfully remove the event of selecting the observed data. In other words, we can, by doing this conditioning, we can remove the data selection bias. And finally, the conditional sampling distribution of the Wasserstein is a truncated normal distribution, which can be analytically characterized and used to obtain the valid confidence interval. So this is the schematic illustration of the proposed methods. So first, we observe the observed data x observed and y observed. Then we apply a linear program on the observed data and obtain the optimal coupling. After that, at the second step, we need to search for the region where the same optimal coupling is obtained. Here, when we obtain for the purple point, we obtain the same optimal coupling as the observed data. And finally, by considering the sampling distribution of the Wasserstein conditional on this conditional space at the second step, we can successfully identify the exact sampling distribution of the Wasserstein distance. So, which is subsequently used to compute the confidence interval. This is all for the proposed method. So this is slide show the experimental results on the synthetic data. So here we evaluate the performance of the proposed methods in terms of coverage guarantee, confidence interval length, and the computational cost. Yeah, in the left figure, the orange line is the naive method, so where we does not correct the data selection bias, and the blue line is the proposed confidence interval. So the naive method cannot properly guarantee the coverage property because obviously it's invalid because it does not take into account the data selection bias. But in the case of method, by doing conditioning, we can avoid the selection bias. Therefore, the proposed selected confidence interval can successfully guarantee the coverage property. The result in the middle plot indicates that the larger the true distance between the source instance and the target instance, the shorter interval that we obtain. So here delta represents the true difference between the source instance and the target instance. And finally, in the results in the right plot shows that the proposed method also has reasonable computational cost. And this slide shows the experimental result on real data. Here we consider the breast cancer dataset and lung cancer datasets, and the setting is as follows. Given a dataset with two classes, class 1 and class 2, we either choose 5 instances from the class 1 and 5 instances from class 2, or selecting both source instance and target instance from either class 1 and class 2, then compute the confidence interval. And we repeat this process up to 120 times. So this is the result on breast cancer dataset and lung cancer dataset. So this result indicates that the confidence interval of the Wasserstein distance in the case of different class is shorter than the one computed in the case of the same class. So this is because when the data are different from the different class, so the Wasserstein distance tends to be larger than the one computed in the case of the data are from the same class. So this is the end of the work of the Wasserstein as a conditional selection for the Wasserstein distance. So here are the summary of my presentation. So reliable machine learning is one of the most important issues in the machine learning community. Traditional method cannot be used to evaluate the reliability of the data-driven machine learning result. Conditional selection is a promising approach for statistically quantifying the reliability of the data-driven machine learning. So in this study, we propose an exact non-asymptotic inference method for the Wasserstein distance based on the concept of conditional selection inference. And this is the first method that can provide a valid confidence interval for the Wasserstein distance with finite sample coverage guarantee. So finally, the take-home message is that to quantify the reliability of data-driven machine learning, we need to correct the data selection bias. And the main concept of selecting inference is that by conditioning on the data selection event, we can avoid the selection bias, and it's applicable to the case of Wasserstein distance. In the case of Wasserstein distance, the optimal coupling is data-driven. Then to remove the data selection bias, we can conditioning on the optimal coupling, and then by conditioning on the optimal coupling, we can derive the exact sampling distribution of the test of the Wasserstein distance. So which then we can compute the confidence interval for the Wasserstein distance. Yeah, so that's all for my questions. Thank you so much for listening. So if you have any questions, so I'm very happy to answer and discuss.
Thank you very much.
Yeah.
So may I first ask a question?
Yeah, sure.
So I think selective inference is a quite interesting concept.
Yeah.
But the first paper has been published already more than 5 years ago.
Yeah.
So I think the methodology has been already improved a lot. But how is the practical applications? Do communities of physics, medicine, so do they accept selective inference in their community?
At the moment, I mean, I think are changing, and I think they are changing, and they are trying to accept that, because that
when they publish papers, do they use p-values obtained from selective inference rather than t-test?
I think yes, because that if they use machine learning method, then they need to apply. They need to because when they use machine learning, they will need to using some statistical inference method for the machine learning for the data-driven area. So one possibly, and they use the asymptotic method, and now selection inference method is another method that is not asymptotic, and I think that they can use selection inference as the
I understand. So in principle, using selective inference is more appropriate, but it's a kind of rule of the game, right? Do they change their rule?
I would say
require authors to use selective inference to validate their result.
I would say that not yet popular. So so we need to show them the importance, and I hope that they are now changing.
Okay, thank you very much. So then, any other question? If there's a question from the EPFL side, can somebody speak? But how many people are there in EPFL?
So maybe we can show the room right now. This part people are not sitting because it's within the visual zone. So trust me, there are people. I think maybe more than 30 current.
That's great.
Yeah, so they're hidden and crouching. So yeah, there are more people. The room is pretty big. Yeah. So questions, any questions from here? I think we should have some sort of so we will discuss this. So maybe initial questions from the side that gives the presentation, then we can have the remaining questions from the other side. There is one question from Guillermo.
Hello, thank you for your very interesting talk. I have a question which is a bit of a naive question. So, I mean, the methodology of conditional selective inference is quite elegant, but at the same time, so this is all relying on conditioning on the set that you construct.
Yes.
Right. So in this, if let's say you were trying to use another method, like for example the bootstrap, to obtain a confidence interval for the same quantity, like through resampling, you would probably have find different matchings between the different data point sets, right? So, like, could you comment on essentially how this methodology affects the intervals that you're in compared to other approaches?
Okay. So thank you for your question. So so in my understanding, so for example, if you use bootstrap or something, so you cannot like so first the main advantage of by using the conditioning in selection is that we can obtain the exact sampling, not approximation, but exact sampling distribution of the exact sampling of the test statistic. So which means that we can derive the sampling distribution in finite sample size. Or yeah, but if you use another method, for example, non-asymptotic approach, so you cannot have maybe when you have few data, you cannot successfully derive the sampling distribution of the test statistic of the quantity. So the main difference is that by doing conditioning on the selection, we can derive the exact sampling distribution of the test statistics. So which means we can make the exact inference rather than non-asymptotic inference. So that is the main advantage of the conditional selection inference. So that's my answer your question.
So first, I'd like to thank the organizer of the workshop. I'm Yu Zhe. Today, I will introduce our work, domain generalization, where adversarial learned level domain. The success of the machine learning algorithm largely depends on assuming that the training data and test data are independent and identically distributed. However, in reality, this IID, also we call this IID assumption. However, in reality, the IID assumption may not hold. Oh, sorry. Okay. So in this paper, we wanted to improve models performance when the IID assumption doesn't hold. And there are a lot of settings consider this task. In this work, we consider the domain generation task. And also we will introduce in the previous solutions and limitations in these sections, the background sections. Okay, so as I said, in this work, we wanted to improve model performance when the IID assumption may not hold. And in reality, this will happen a lot. This will often happens. One example is like, for example, we can collect the data in hospital 1, and we're using this data to train, for example, a cancer detection models. And when we have such models, we want that the model can be used in a lot of hospitals. For example, we want to apply these models in hospital 2. In these situations, since the hospital 1 and hospital 2 have some difference, for example, the device or patient are different, then the data will have different distributions. In such case, the IID assumption may not hold. And when this assumption didn't hold, the performance of the machine learning models may decrease significantly. Okay. And in this work, we consider the domain generation task to improve models performance when the IID assumption didn't hold. For these settings, in the training phase, the model is trained on the multiple domains, which means, for example, in the following pictures, we have 3 domains: photo, sketch, and cartoon. And in the test phase, we want the trained models can generalize to unseen domain. For example, we test the trained models on the art domains. And I'd like to remark that the art domain will not include in the training domain. So this is an unseen domain for the classifier. And the data augmentation is one of the most common way to solve the domain generation task. And we focus on two types of the data augmentation strategies. The first is the adversarial data augmentations. It attempts to augment the training data with difficult samples. And we can also consider these samples are drawn from the worst case distributions. Usually, the previous work used the pixel level perturbations to generate the worst case samples. It's like very like the adversarial attack. And the paper one shows that the augmenting the samples from the worst case distributions can improve models' domain generation abilities. However, as the example shows, when we consider the domain generation task, the difference between domains are very large. However, using the pixel level adversarial attack, we can only obtain the samples that with similar semantics with similar styles, as the latter figure shows. The first row is the original training data. The second row is the training data generated by the pixel level perturbation, pixel level adversarial attack. We can see there are no significant difference from the first row and the second row. Another strategy is called the generative model-based data augmentation. It attempts to synthesize the training data by generative models. This method often focuses on the increasing the diversity of the training data. As the left figure shows, each figure is one of the training data. We can say the style of the training data can change very differently. And however, the limitation of this method is that this work have never considered the data accommodations with the worst case distributions using the generative model. Since the paper one already showed that difficult samples were helpful for the DG task. So in this work, we want to combine the advantage from the both adversarial data accommodations and the generative model-based method. And more specifically, in this work, we want to synthesize images that become more and more difficult during the classifier training. And we want to synthesize the images become semantically different from the training domain. So then I will introduce our solutions. So overall, we aim to control the data generating distributions represented by our generative models, so that it can generate hard samples. And then we want to train the classifier theta F with these samples. So the overall objective is showing the following. In the inner part, we want to control the data generating distribution PG, so that the loss value of the classification loss will be maximized. And in the outer part, we want to optimize the theta F, so that the loss function, the loss value is minimized. And here, one difficulty is how to control the generative model's behavior, which means how we affect the PG. So our idea is to utilize a specific image-to-image translation models below. So to control the behavior of the generative models, we utilize these DLO models. The DLO model is a very special image-to-image translation models, and it's like the following equation shows. For a DLO model G, it takes two input. It takes two things as input. One is the original image X. One is a domain code. We call it domain code Z. And output are images X prime that the style specified by the domain codes. In the left figures, we show several samples of the domain codes. These figures are all take one one sim X is input, but you can see by utilizing different domain codes, the style of the images can be very different. However, empirically, we will find the original Dilo models has some limitations. That is, original Dilo models can only generate images with limited diversity. And we will use the following simplified examples to explain why this happens. So the Dilo models is built on the cycle-GAN models. The cycle-GAN models is the red. One example of cycle-GAN models is showing on the red figures. Here, the X and Y are two different domains. And we have in this models, this models has four modulars, two generator G and F, two discriminator DX and DY. The generator G can transfer images from domain X to the domain Y, and the generator F can transform the images from domain Y to domain X. In the cycle-GAN models, they have a very special loss functions to ensure that the generated images can maintain the semantics. This loss is called the cycle consistent loss. The basic idea of this loss is that when we transform the image X from the domain image from domain X to domain Y, and we can when we recover that transferred image between from domain Y to domain X, the distance between the FGX and X should be minimized, which means we can recover the original images from the transferred images. And if we can achieve this, which means we already maintain the semantics. However, the paper one shows that the cycle consistent loss will limit the diversity of the generated images. Since the Dilo model is built on the cycle-GAN model, which means this also is the reason that can limit the diversity of the Dilo models. Hence, we follow the paper one strategies, use a weak version of the cycle consistent loss to replace the original cycle consistent loss. The main idea of the new cycle consistent loss is that instead of forcing the generated images can be recovered, we now enforce the feature extracted by the discriminators can be recovered. So this equation shows this has two terms. For the first terms, we want to enforce the feature level recovery. We want the features extracted by the discriminator DX can be recovered. And in the second term is like the original cycle consistent loss. We force the pixel level recovery. So with this new cycle consistent loss, we find that the diversity of the synthesized images is improved. Is the red figure shows. The left figure is the original Dilo models and its output. The red figures is the Dilo models with new cycle consistent loss. We can say although the inputs are exactly the same and the training data is exactly the same, when we changing the loss functions, the diversity of the generated images can be improved a lot. Also, empirically, we find that improving the diversity is helpful to improve the domain generation ability. Hence, in this work, instead of using the Dilo models, we utilize the new models. We call this model Dilo B. And with the Dilo B models, now we can control the behavior of the generative models by optimizing the domain code distributions. And we propose two strategies to represent our trainable domain code distributions. Then, by optimizing these trainable distributions, we can find the worst case data generating distributions represented by the DLB models. For these two strategies, the first is we're using our trainable denucleated distributions to represent our trainable domain code distributions. And the second, we're using a neural network termed the domain code NN to represent the domain code distributions. First, I will talk the first strategies, the denucleated distributions. Since the domain code are the k-dimensional probability vectors, so it's naturally to first consider elemental distributions. So we consider the denucleated distributions. So we utilize our denucleated distribution B parameterized by alpha 1 to alpha k to represent the distribution, the domain code distributions. And then we can optimize the domain code distributions by optimizing the alpha 1 to alpha k to find the worst case distributions. And the advantage of this strategy is that fewer parameters need to be optimized. Because here the large k is the number of domains. In the domain generation settings, usually the k is not is less than 100. So which means there are very small parameters we need to optimize. And the second strategy is using a neural network termed domain code NN to represent the domain code distributions. Inspired by the GAN, we utilize a neural network small g to represent the domain code distributions. First, we design the last layer of the domain code NN is a softmax layer. That is because domain code is a probability vectors. Hence, to make the output of the G is valid domain code is a valid domain code. So we need a softmax layer. And like the GAN, we take the Gaussian node C as input, so that the output can represent the domain code distributions. The advantage of this strategy is the better representation abilities, because it can represent more, hence it can represent more complex domain code distributions. When the given training domain are very complex, we prefer using the domain code NN instead of the denucleated distributions. Okay, so now I will introduce our main framework. So with the above idea, the domain, the way to the generative models and the way to represent the domain code distributions, we now propose our data augmentation method, the generative adversarial domain augmentations. Because we have two strategies to represent the domain code distributions. So in here, I utilize one of them to give explanations. So there are three modules in our proposals. The first is the domain code NN small g. And this part is used to represent the domain code distributions. And this module can also be replaced by our trainable denucleated distributions. And second is a trainable, is a pre-trained DLB models. And the third is the mean classifier F. We will use F to do the classification task. And our mean object function is shown in the following. Basically, we wanted to solve the following min-max optimization problems. And to solve it, we alternatively do the inner maximization and outer minimizations. We first maximize the objective with regard to the small g. In this part, we want to find the worst case distributions of the domain code. We find our worst case domain code distributions by optimize the theta g to maximize the loss functions. And then we minimize the objective with regard to the theta f. In these steps, we want to train the models over the worst case distributions. And then we repeat above 2 steps. Okay, then I will introduce some experimental results. So first, we consider experimental settings that we only have the limited computing resources, which means all general hyperparameters. Here, the general hyperparameters means the type of optimizers, the narrators, and some other parameters that were used in the most of machine learning algorithms. For this general hyperparameters, they are all set as consistent values for all proposals and all commutators. And for hyperparameters that are only needed in all methods, we tune them with limited trials. So this too is because we only have the limited computing resources. And the first experimenter is test all proposals on 3 common benchmarks. And in this page, I first show the result on 2 common benchmarks. One is called the digits DG. This benchmark have 4 different digits data set. And the second is the PACS data set. It also have 4 different domains: the photo, sketch, cartoon, and art. And to apply this experiment, we utilize a principle called leave one out principle, which means we first choose 1 domain is the test domain, and using the rest of 3 domain is the training domain, and train the model and test accuracy. And first, on these 2 data sets, on the digit data set, all 2 proposals, JDD, that means all proposals with the Dirichlet distributions, and JDNN, which means all proposals with a domain code NN, achieve the best performance among all commutators. And for the PSA data set, all result is close to the state of art method MBDG. And the third benchmark is the Office Home dataset. It also have 4 domains, and also we follow the leave one out principles to apply to conduct the experiments. And I'd like to say, in the overall, in average accuracy, all methods didn't have some advantages over the other commutators. For example, the Yang, and but by comparing the performance of the ERM method, the ERM here, ERM is empirical risk minimizations. By comparing the performance of the ERM on each domains, we can judge the difficulty of each domain. So on the Office Home dataset, the most difficult domain is CLIPAT, and on the digits DG, the most difficult domain is MSM, and on the PCS, the most difficult domain is Sketch. We can find, instead of the MBDG on the Sketch domain, on all most difficult domains, all proposals achieve the best result. This indicates that all proposals is better at handling the difficult domains. This also fits the design of all proposals. We want to train the models on the worst case distributions. And also, we visualize all 2 proposals. We visualize the generated images in each steps and the domain code distributions during the training. And is the red figure shows. The top is the result of the visualization result of the GDNN, and the bottom is the visualization result of the GDD. We can find the generated images become more and more difficult intuitively, that MNIST images should be the most easy domain in the digits task. The images become more and more colorful, indicate that the samples become more and more difficult. So this is the first thing we can find in the visualization result. The second is that we can find the GADD is easier to optimize than GADNN. For example, in the step 3000 and 4000, we can find the proportion of the colorful images is larger than the proportion of the colorful images in the GADD is larger than the proportion in the GADNN. And also, we can see the domain code distributions. The GADD quickly converge to a very small space, but the GADNN still on a large space. And also, we check the importance of each modulus in our proposals by the ablation studies. We apply the following ablation studies. First, we test the importance of the generator models. We use a pixel level adversarial attack to replace the generator models. And second, we test the importance of the worst case distributions. We're using the non-adversarial distributions of the domain code to replace the learned adversarial distribution of the domain codes. So here we're using two distributions. One is uniform distribution on the simplex. One is the logistic normal distributions. And three, we test what happens if we do not use a domain code NN. We replace the domain code NN by adversarial optimizing the domain code directly. Kind like the adversarial attack, adversarial training. So this here is the result of the ablation studies. And here we can find the result of the proposals. This result shows that each modulus is important in our framework. Also, the paper one shows that the hyperparameter selections is very, very important for the DT task. Hence, our previous settings that assume that limited computation or computing resources may be not suitable for the DT task. Hence, for the better comparisons, we also conduct an experiment under the settings that we have enough computational resources. And since we have enough computational resources, we first random set the value of all hyperparameters from our uniform distributions respectively. And then we train our models by our proposals, and we repeat this process 20 times. We will have 20 set of hyperparameters, and we evaluate these 20 models on the training evaluation set and choose hyperparameters that achieve the best validation accuracy is our final hyperparameters. And with the fine-tuned hyperparameters, here the F refer to the fine-tuned. We can find all proposals, the performance of all proposals increase very significantly. Also, compared with the state of also all proposal GDNN can achieve better performance than the previous state-of-art method MBDG under these settings. Okay, so now to sum up, in this work, we consider a data augmentation strategies that we consider the data augmentations with the worst case distributions using the generator models. And all proposal JDA, we utilize a pre-trained DLB models whose behavior is conditioned by the domain codes. And we propose to learn a trainable dynamic distributions or domain code NN to represent the distributions of the domain codes. we empirically evaluate all proposals on the different datasets, and the experimental result suggests that the GDA effectively increases the model's generation abilities. Okay, thank you. So, do anyone have some questions?
Okay, thank you very much. Any questions? So let me start. So can you say something about the computation time compared with some basic approaches?
You mean computation time compared with the previous work?
Yeah.
Actually, there are no large difference between our proposals and the previous work or the previous method. Maybe the most for the training time, the most of the time will be used to train the DLO models. For when we train the classifier, the time actually you can see the training objective. The training time actually, the training step is same as the previous method. So the training time, there are no large difference between our work and the previous work, our method and previous method. And also, in my understandings, so because what we want to solve is a classification task, and maybe in the understanding of ours, in all understandings, the training time may be not important in this task, because we just want to train a classifier, and this although if the classifier training the classifier takes a lot of time is not acceptable, but for example 2 hours and 3 hours there are no such difference. Is because the model, the training, after we finish the training, when we test the models, the test time should be the same.
Right. So what about the number of hyperparameters? Are they also the same?
Actually, in our training objective, we do not involve some another hyperparameters. Hence, for the hyperparameters, in our training objective, we only have one hyperparameters to balance the trade-off between the model trained on the Wasserstein distributions and the model trained on original training data. So we do not have a lot of hyperparameters in our work.
So the number of hyperparameters is the same as previous methods, or do you have more hyperparameters?
Because for different methods, they have different number of hyperparameters. Right. I can just say for some method we have less hyperparameters, but for some method we have more hyperparameters.
Greetings, ladies and gentlemen. Today I'm going to introduce our work named Expert Advice Problem with Noisy Low Rank Loss. My name is Liu Yaxong. Now I'm PD researcher in RIKEN-AIP Computational Learning Theory team, leading by Professor Hatano. Okay, this presentation is composed by the following parts. Firstly, I'm going to introduce some basic definitions in the titles. What is expert advice and what is low rank? Then I'm going to interpret the solution of these problems, especially in the fourth section that is the main result of our work. Then it follows the experiment and some notice about the future work. Okay, let's come to the first part. This is about the definition of prediction with expert advice, which is a very famous online learning model. And in this model, there are two objects in this framework, algorithm and the environment. It is a sequential decision-making systems for round small t from 1 to capital T. In each round, Firstly, the algorithm gives n-dimensional distribution WT, and then the environment returns a loss vector LT. It is in -1 to 1 cube n-dimensional. I want to give two notice about these issues. Firstly, the loss vector can be adversarial, which means it is not necessary to be IID distributed from underlying distribution. And second is that for each round, the algorithm firstly gives the distribution and then receives the loss vectors. So this is a prediction problem. Then for each round, the algorithm incurs the loss, the inner product between prediction distribution WT and the loss vector LT. The goal of the algorithm is to minimize the regret, which is a difference between the simulative loss and the global optima in hindsight. And as we mentioned, this is a very traditional online learning model, which has been researched for decades. I think one of the very famous algorithm is called Hedge algorithm in point paper in last century. It gives upper bound to this regret. Meanwhile, this bound is also tight, which means that the upper bound and the lower bound only differs from each other with a constant parameter. And this regret is theta as square root of t times log n. N is the dimension of the loss vectors. Okay, now let's come to the noisy low rank structure. Firstly, we introduce what is a low rank structure. We introduce this issue with an example. Let's consider movie recommendation systems. There are n different movies, and we evaluate these movies with d different factors like music, casters, stories, directors, and so on. And then there are t different users. For each user, we represent them as also a d-dimensional vector Vt. And we can say that each vector, users Vt, they will evaluate these n movies with inner product as ui times Vt. So in the loss vectors Lt, the ith entry of the vector represents the negative scores of user t to the movie I. So in this case, if the environment is in this way, so the regret now can be seen as the expectations of the simulative negative scores from the algorithm and the favorite single movies for all the users. So now, as we mentioned before, that there are although there are n movies, but there are only d different factors for these movies. So we can call that the loss sequence t from 1 to large T is a d rank loss. So this is not a very straight definitions. Let's come to a more formal version of this loss. Okay, although the loss vector Lt is an n-dimensional vector, but actually all these loss vectors are from a d-dimensional subspace from the n-dimensional space. So given matrix U, which is the rank of this U is D, we call this as a kernel of the d-dimensional subspace, which means that each loss vector can be seen. It is linear combinations of in this d-dimensional subspace. Okay, and if the rank or the rank of U or the kernel, the rank of the kernel is very small, much smaller than the dimension of the loss vectors, we could call the loss sequence as low ranked. But precisely how small this D should be? Well, from the following part, we would say that D should be in the order of square root of log n. It must be quite very small. And frankly speaking, the noisy low rank loss is straightforward, that for each low rank structure U times Vt, we add arbitrary noise vector epsilon t, and now we can have a noisy low rank loss. One thing I want to mention is that no matter how this noise vector is, the D rank loss vector has been totally damaged. So if we have a review of the movie recommendation systems, we can say that now the negative scores of user I to the movie, user T to the movie I will added noisy part epsilon Ti, although all the epsilon Ti is bounded with L2 norm. I think this is more natural because there will be some interpretations of the users. There have some influence, like emotions for him to his attitude to the movies. So if we say the rank of the loss vectors is n and the noisy part disappears, then our setting recovers the original expert otherwise setting that all the loss vectors are arbitrary. And if the epsilon is 0, and which means that there is no noise, it is recovered the low rank case. Okay, now we can describe the definition of expert otherwise problem with noisy low rank loss. Fix a full rank matrix U. For each round, algorithms firstly makes the prediction WT, and then the environment gives the loss vector LT. It is composed by two parts, the low rank parts U times Vt and epsilon T as a noisy part. One thing that we need to mention that the algorithm only receives LT, so the algorithm has no information about U or epsilon T, but algorithm know the upper bound of L2 norm of the noise. And then the algorithm incurs a loss with respect to the noise low rank loss LT and its prediction WT as inner product. And the regret is also defined with respect to the noisy part, noisy loss vectors, LT. Then I will show the location of our work. This online learning expert otherwise problem with low rank loss is a quite new topic rather than the original problem. And we can say that if the kernel U is known to the algorithm, then the result is quite nice. That, for instance, it is tight as square root of D times T, or even though it is noised by epsilon, it has also a square root of D plus epsilon T bound. And if the kernel is unknown, then the upper bound is D times square root of D. So our work is to consider the case that the kernel is unknown and the low rank structure has been somehow damaged. And this is our work. We gave the regret bound as square root T times D plus the second part. And we can say that if the epsilon is quite small, for instance, it's in order of 1 over n, and the rank is in the order of log n with power 1 over 3, our work can be seen as accurate than the hedge algorithm. Okay, let's have, before to our main result, I want to have a review of the previous work about the noiseless case. And the basic algorithm used for both noisy and noiseless cases online mirror descent. And we will involve the matrix norm here. And this theorem shows that the regret is respect to two parts. Firstly is bound to the matrix norm of the domains. And the second part is dual norm to the loss vectors. This is about a little bit technical part that we will use minimal volume enclosing ellipsoid, which means that we will, as the input of the k different independent vectors and intersect it with L infinite norm, it will output ellipsoid, which contains this subset of the loss vectors. Meanwhile, constant times this ellipsoid is contained by the previous mentioned subset. And we will use this ellipsoid M in our result. Okay, this is a basic reduction if the kernel is known. Compared with the Hedge algorithm, the decision set bounded with L1 norm is 1, and L infinite norm is 1 actually. Then with the low rank case, the decision set is bounded with respect to the rank of the kernel, and the loss space here is bounded by 1 actually. So this theorem shows that if the kernel is known, according to online mirror descent, the regret is given as square root of d times d. So we can say that in this case, the regret bound is highly related to the rank of the loss sequence. And so if the kernel is unknown, the result is also not difficult. We can use inductions that firstly, we show that we assume that the kernel is empty set. Once the received loss vector cannot be represented as the current subspace, then we just add this new loss vector as the new kernel. Then it gives the regret bound as d times square root of d. However, this algorithm fails if, as we mentioned for the noisy case, because in this case, the rank of all the noise vectors is not d anymore. It's the rank expands to n. It's the full rank matrices. So if we run the previous algorithms, the result would be n times square root of t, which is too large for these parameters. And Barman in 2018, they gave some algorithms to solve the case that the kernel is known but noised by the noise vector. So our setting, we assume that the noise is given to corrupt the low rank structure. Meanwhile, the kernel is unknown. So how could we approximate the true kernel? This is one of the central problems in our paper, and we need to solve. In principle, we will give our selection criteria for selecting the receiving loss vectors. There are actually two criteria. Firstly, we will make sure that the loss vector is long enough respect to the L2 norm by involving a parameter as k. And secondly, we will choose that the loss vector is far enough to the current span space, which by involving another parameter gamma k, which means that we will select the loss vectors, which is long enough, and it is highly independent to each other to compose or to approximate the true kernel U by UK theta. And we can update the k by the receiving loss vectors until then. So compared with the previous work, we can make sure that firstly, during our selection criteria, the algorithm will only update it for the approximate kernel for at most large k times, which we can guarantee that this capital K is smaller than the true rank of the loss vectors. So now we can make sure that the decision set actually is bounded by the collected loss vector number of collected loss vectors, and the loss space now is bounded by in this way, mk is corresponding to the parameters sk and gamma k. Therefore, multiplying the mirror descent algorithm, we can get the regret bound in equation 7. And in this experiment, we show that with different noise, the performance of our algorithm and Hassan's algorithm and Hedge algorithm, we can say that if the epsilon is 0 without noise, our algorithm actually performance is same as Hassan's algorithm. And if the noise exists, our algorithm performs much better than Hedge algorithm and Hassan's work. And with different n, which means with different number of experts, our algorithm performs also better than Hedge algorithm, for instance, with epsilon is 0.8. In the future work, we hope to remove the parameter n in the regret bound, or show the lower bound must contains n, or we hope consider other kinds of noise vectors, for instance, sphere loss vectors, or the loss vector is sparse. Okay, thanks.
Okay, thank you very much. Are there any questions? Then let me start. So actually, I wanted to ask a question about experiment.
Okay.
So like t equals 1000.
Yes.
Is it large enough for the theory to be reliable?
Yeah, yes, this is just a toy example, actually. Actually, during the programming, our algorithm, it takes much time than other algorithms. So this is just a trend for the experiment. Actually, if t is larger, I think our algorithm can also perform us, because we can offer an theoretical regret upper bound, actually.
So then when t is 1000, maybe it's not big enough. Then so perhaps error bars are quite large.
Yes. Actually, the theoretical result shows that the error should be not very large. So we can have this regret bound. But I think if, as we can say here, if epsilon square is bounded by the minimize of this part, and actually in our case, the d must be in the order of square root of log n. So I do believe that even the epsilon as a noise is a little bit large, our algorithm can also perform as not worse than Hedge algorithm or Hassan's result.
So of course this is a theory result, but so in practice, so how like useful the upper bound is?
In practice, I just suggest to running our algorithm with Hedge algorithm parallel, because we cannot make sure that what's the rank, the number of the rank in other ones. So our algorithm can perform us only when the rank is smaller than square root of log n. Then the low rank algorithm or the low rank structure effects. Otherwise, Hedge algorithm is better.
I see. Okay, thank you. So Chibin.
Yeah, I have a question. So when you learn the kernel, when the kernel is unknown, I think
yes.
you expect to have low rank, which means smaller d. I'm wondering, how do you learn the optimal d, optimal rank, And another question is there any relationship with low rank matrix decomposition?
I think about the first question, our algorithm is designed for the case that there is no prior information about the kernel, which means that at the beginning of the algorithm do not know the rank of the kernel. So the D can be expanded to N, but our algorithm also can performance. But as I mentioned before, if the rank of the loss vectors is not so low ranked, actually, for instance, the rank is half of N, then I suggest to use H algorithm. Our algorithm only affects when the rank is very small, and we can guarantee theoretically that the updating times is bounded. It will not larger than the rank of N, the rank of the kernel. And as for the second question, I think it will be applied somehow in the proof of giving the bound to the the dual norm of the loss space with respect to the matrix decomposition. Here it will have some in the proof of this part, I think the matrix decomposition will be applied here. Does this answers your question?
Yes, thanks.
You're welcome.
Zhao Kai?
Hi, thank you for your talk. I have a question regarding your previous comment on running parallelly the hedge algorithm and your algorithm.
Yes.
I'm wondering if we can have I'm wondering if we can have a method that no matter how large D is, we can perform optimally, which means that if D is very small, then it will achieve the regret bound you give. And however, if D is larger, for example, in the order of capital N, then it will automatically recover to the hedge algorithm, the bound of the hedge algorithm. In this way, you don't need to run parallelly two algorithms, and you will have one algorithm for all the cases.
Okay, this is actually, I think, nice future work direction. Actually, if we're running a meta algorithm with experts, as there are two experts, one is our algorithm with low rank, for instance, Hassan's algorithm. Another one is hedge algorithm. So in this meta experts predictions, I think the result can also convergence to the best case of either two situations.
Then can you briefly explain how this meta algorithm choose between the predictions from these two sub-algorithms?
Okay. Let's consider the expert advice of these meta algorithms. And we can set in this meta expert advice, we can set only two experts. One expert is giving the result with the hedge algorithm, and the second expert gives the result as a low rank algorithm, for instance, our algorithm or Hassan's algorithm. Then for this meta expert advice, we can use hedge algorithm, which will make sure that the best choice has only square root of t difference to our choices.
Okay, I see.
There is only log 2 difference because the number of x has 2.
Implementing the meta algorithm by a hedge algorithm can automatically choose which one is the best, and the additional cost won't be too large.
Yes.
Right.
Yes.
Thank you so much.
You're welcome.